Long time no see.
What has it been? Like an hour?
What's that?
How long has it been? Like an hour?
Yeah.
How you been? What's changed?
An hour and 15 minutes.
What's new? Hey, we're in early.
Hey, we have a class.
If you make no selections within 30 seconds, you will be recorded. Everything good?
I was gonna put this on. Just so annoying. Let's switch to the local PC so you can see what I'm putting up with. So when I create a new module in Canvas, you create a new module, immediately publish, and you have to remember to click here to publish it. So I thought I put this up for you guys so you could see week 11 reading notes of these videos. You know, created this module over the weekend on Friday, and I thought everyone could see it, and I now just realized that you couldn't have. But it's not that big a deal. It's just annoying because I thought I remembered to click that. Okay, so
In an AC circuit, the voltage and current keep changing direction.
Hey, students in Pullman, can you hear
can
this
hear the
video?
sound.
Is it playing all right?
Yes.
Yes.
The voltage is the energy for charge, and we can
We
visualize.
can hear it too, aren't you gonna ask?
I didn't see that you guys had, that your call had come in yet, so I was just wanna check with one
Fine,
group.
I'm leaving. Just kidding.
Aww. I feel bad, now you made me feel bad. The goal was to make Dr. Taub cry, mission accomplished.
Oh, no.
I don't know.
I don't know if I can do it again.
It's a 50-50 shot.
No, it was 100% shot last time, but now it's a 50-50, so.
Four oh one, 406, 416.
If you don't decide.
I can't say no again, because he always shows up before Dan does.
I'm bent on Dan. I'm relying on him.
Oh, that's your daily bet on who walks in the classroom.
Yeah.
I forgot who else is in this class.
Oh, Caitlin. Oh, you're Wyndham?
I don't know any other names. Who is the tall guy? Lady, apparently.
Made it on YouTube. Research or something.
I like it.
So far.
I almost said Jeff. He's not in this class.
Oh, I could have just searched him. Both listening away.
Yeah.
Are you taking applied aerodynamics?
Hey, did I just hear some people talking about maybe taking applied aerodynamics?
Yes. I was thinking about it.
Did you know when it's supposed to be offered? Like what time of day and what days a week?
I think it's the one that you're teaching is apparently being offered to Fulmer.
Yeah, no, I am teaching it, but they haven't told me when I'm teaching it, so I'm curious if we
Monday,
do.
Wednesday, Friday, 3 to 4.
3 to 4? Okay, thanks.
Pretty.
I specifically asked
Oh,
for
let's
Monday,
go! Let's go!
I specifically asked for Monday, Wednesday, Friday, but I didn't. Oh, who won?
Oh, yo. Someone
Okay.
lost a bet.
All right, I've got 4:15. Let's get going. So some bookkeeping stuff. The exams, I just got the exams from Pullman this morning, so I have not graded them. I'll block off all of tomorrow afternoon to grade the exams. If I get the exams graded by the end of Thursday, and that really is a big if, I'm going to try. And I can get them scanned back to Bremerton and Pullman, so by Friday's class, everybody can have their return exam with them, and we will go over the exam on site. If that's not done, or I don't get things done in time, but I can get things scanned to Pullman and Bremerton, then we're gonna have to wait till next Wednesday to go over the exam. As is, I have, other than flipped through a few people's exams, I went, at least, one of the presidents, oh, you got everything right on this problem, or they went astray on the other problem. I haven't looked at them, I don't know how, I don't have a sense of like where the class, how the class did yet. So I will have a much better idea on Friday, and hopefully we'll be able to go over the exam on Friday. Another thing, I realized, the day that I stated, everybody had to have their, group requests in. I stayed late that night and went through it and made sure everybody had a group. But all I did was, if you said you had 3 people in your group, I didn't send an email saying, yes, this is your group. So I'm assuming everybody understands that if I said I wanted to be in a group with 3 people, those are your 3 people. The people who requested a group said, I need help finding a group. There were enough people who said specifically, we would like a third, or we are open to having a third, who said that I was able to pair them with. I sent everybody in that situation an email. So if you were looking for a group, you should have received an email from me about 2 weeks ago saying, and CCing with the other 2 people saying, you 3, please work together. So if you're still confused about who your group is, you shouldn't be, and you should have received an email from me. Again, whatever day that was, I said was the deadline. It was like Friday, or like 2 weeks ago, I think, or a week and a half ago. Okay, so everybody should have their group. Another small thing, somebody emailed me right before class today and pointed out to me on the project, part 1, where I give the power curve and I give a piecewise function for the power curve, that all my inequalities were pointing in the wrong direction. I just fixed that. I don't think that's going to trip anyone up, but obviously it's not producing power at less than, not greater than 5 meters per second. All right, so I think that's all I have as far as bookkeeping goes. We are starting a new chapter today. We are starting chapter 5, and I just posted this on Canvas. I posted chapter 5, and I also posted in that Canvas module a list of videos, YouTube videos that I think will be helpful to you guys in understanding these concepts. Some of these I intend we'll watch together as a class when we get to them. I intend to spend no more than 4 lectures on this material. Okay, so 2 weeks. Today, I'm hoping to go over some basic concepts of AC power. And a little bit about 3-phase power, and probably on Friday, we'll cover fundamentals of electromagnetism and get into, and at least start, the basic operation of how different types of generators work. There's several of them. There's DC generators, there's also, there's AC and DC generators. Within AC generators, there are synchronous generators, there are asynchronous generators, there are induction generators, which is really just another word for asynchronous generators. There are also some other more novel types of generators that I'd love to have time to talk to you guys about, but we'll have to see how it goes. And then that is probably going to take us Friday, and we'll probably continue to be talking about that next Wednesday. And then whatever time we have left, we'll talk about electrical aspects of variable speed turbines, some other equipment, electrical equipment. And one thing I'd really like to end with is, how does the need and the torque requirements of the generator pair with the torque and the speed being delivered by the rotor? One of the most important things to try to match is what the generator wants as far as speed and torque, and what the rotor is delivering in terms of speed and torque. Okay, so with that, we're going to start with our first topic, basic concepts of AC power. And I'm going to work under the assumption that we don't need to discuss basic concepts of DC power. That you guys are familiar with voltage, you understand what current is, you understand what resistance is, you understand what conductivity is, you understand basic DC circuits. You may not remember if it's VIR or IVR, but you know Ohm's law that relates those 3 things. That you're familiar with Kirchhoff's laws, capacitors, inductors. You understand resistors in series and resistors in parallel, and how those work.
I got a question.
Yeah.
So homework 4 is due this Friday?
That sounds right. Yeah, that's what the students reminded me yesterday, that it was due on Friday. Yes, that's right.
Okay.
It should not be as scary as homework 3.
Yeah.
I don't think.
It's more terrible.
I mean, was that?
No, I'm joking.
I mean, I don't want to be like, oh, that's great, I'll wait till the last 30 minutes to turn it in. But it shouldn't take you as long as homework 3 did. Homework 3 was probably the bulk of this class. And what that was the aerodynamics homework. All right, so basic concepts in AC power. First off, in AC circuits, both your voltage and your current are sinusoidal. And I don't know how much, we're gonna get into some weeds here, and I don't know what you guys have seen. I know you guys take circuit classes, and I don't know how much of this you've seen already or not. I think at this point, you guys probably all know that in AC circuits, your current or your voltage, at least one of them is sinusoidal. That's why we call it AC, right? And you probably know that if you're here in the United States, the frequency is 60 hertz. And for historical reasons, if you're in Europe, or most of the rest of the world, if you're not in North America, the frequency is 50 hertz. And I don't know why I drew an extra line there. This is supposed to be the output frequency. And so our voltage is a function of time, and it has a maximum amplitude, so we'll call it voltage max, times sine of 2 pi times the frequency times time, plus some phase shift. So this phi here is my phase shift. And just kind of remember that 2 pi times frequency in hertz is equal to angular rotation, so in radians. And our current is also sinusoidal. And the phase shift between the two is, in general, not the same. In fact, usually when we're looking at this, we're going to assume that one of these phase shifts is zero, and what we're really going to be interested in the phase shift between our voltage signal and our current signal. So normally, this is not the case. Now, a lot of times what we want to know is not the maximum voltage. What we want to know is some concept of the average voltage. So what we look at is what's called the RMS voltage. And the RMS voltage is the square root of the integral over some cycle, at least one cycle, of our voltage squared dt. And what this turns out to be is equal to our Vmax times the square root of the integral of sine squared 2 pi frequency times time. And this turns out to be equal to Vmax times the square root of Vmax times the square root of 2 over 2. I'll write that. So Vmax equals VRMS equals Vmax, the square root of 2 over 2, which is roughly, VRMS is roughly about 70% of Vmax. Okay, so, and this is important because this is kind of like going to give us our average power as opposed to our maximum power. Although, don't think too much about that because there's something else about the amount of actual power, real power we have and the amount of parent power that we have. We'll talk about in a few minutes. All right, now I mentioned that the phase shift between my current and my voltage is not normally the same.
Ideally, we would like it the same, but that's usually not the case. So some of the things that cause the voltage signal and the current signal to be out of phase are the types of elements that we have in our circuit. So we're first going to look at what happens when you have a capacitor in an AC circuit. So if voltage as a function of time is equal to V max times sine of 2 pi frequency t, and I'm going to say for now that my phase shift on my voltage is 0, then my current, which I'm going to use lowercase I, if you remember from, definitely covered in dynamic systems, it's probably covered in a circuit class that you've had before, that your current is equal to the capacitor, the capacitance of the capacitor you're flowing through. Or I'm going to go just
Switch down.
I have a voltage across the capacitor and I have current going through the capacitor, and that capacitor has a capacitance C. The current that goes through a capacitor is related to the voltage through the capacitance of the capacitor times the derivative of the voltage. Remember, the voltage is going to be changing with time. And if my voltage is changing in time and this is its signal, then I have to take the derivative of this. And what this is going to turn out to be is going to be 2 pi f, because I'm going to use the chain rule. So I'm going to have the 2 pi f. I'm taking the derivative with respect to time. And so I get the 2 pi f, and then I have a x that's already out in front. And then I'm going to do some, normally I take the derivative, which would end up with cosine, and then I take the inside, and then I would, I still have the sine in here, and then I would take the derivative and get up with the cosine. I'm going to do a little bit of, I'm going to skip over the trig identities, and what you're going to get is sine of 2 pi f t plus, and you're going to end up with a phase shift of 90 degrees. And so this value out here is now, this is your current max. So this is your maximum current. And the fact that the maximum current is not the same as the maximum voltage has to do with something very similar to Ohm's law. We'll say that I, our current max, is equal to our voltage max over XC, where we define XC as our capacitance reactance. And as you can see, this capacitance reactance is playing the same role, R-O-L-E, as resistance does in Ohm's law. And so here, XC is going to be equal to 1 over 2 pi, our frequency, if I think I did that right. And the other thing to note is the phase shift. So because now the current is 90 degrees ahead of the voltage, we say that in capacitance circuits, we say current leads voltage. Now, what I'd like to do is to do the same thing, but this was for capacitors. Now I'm going to do this for inductors. Okay, so this is inductors in AC circuits. Again, my voltage signal is equal to V max times sine 2 pi f t. And my current as a function of time, and again, set yourself back to either dynamic systems or to a circuits class that you've taken in the past. Now, maybe I should draw one. So now I have an inductor, which we usually draw like this. The inductor has some inductance, which we use the letter L for inductance, because inductance starts with the letter L, I guess. And there's, of course, going to be current flowing through it, and there's some voltage across it. And so the relationship between voltage and current in an inductor is that I is equal to 1 over L, the inductance, times the integral of your voltage over time. And so now this will result in V max over 2 pi when I take the integral of this voltage. So we end up with a 2 pi f over L times sine 2 pi f t minus pi over 2. So now, the same relationship before, I say that I is equal to my voltage max over, and I'm going to call this XL, whereas here I called it XC, and I call this the capacitance reactance. XL, so I'll finish writing this. Where XL is equal to 2 pi ft, and this is the inductive reactance. And it also plays the same role as resistance does in a DC circuit. And we say that in an inductive circuit, we say that current lags voltage. Now, real circuits are going to have some induction, and they have some capacitance in them. So in the case when it's just a circuit that just has a capacitor in it and no inductors, it's simple. It's just current leads by 90 degrees or by pi over 2. If it's a purely inductive circuit, it's simple. It just current lags voltage by exactly pi over 2. In an actual circuit, there will be it will depend on the relative sizes of the inductance and capacitance in the circuits, and we're going to do an example like that. And I'm just curious, this one, is this stuff you guys have seen? Have you guys seen this specifically before?
Very vaguely.
No? Okay.
Probably where we start tuning out voltage class.
I know we do not go into this in dynamic systems. I wasn't sure whether it was covered in.
It was probably covered in circuits.
Yeah, probably like the last 3 weeks.
Okay. Something else you guys have probably not seen before, or you may have seen just lightly touched on before, is something electrical engineers really like, and that's called phasor notation. Okay, so you're nodding with your head in phasor.
We covered that in 466.
What's that?
And we covered that in 466 last week.
Oh, right, oh, in your review class?
Yeah.
Okay. Was it review?
Yeah, I actually do remember that.
Yeah, okay.
Yeah.
Okay. So we'll go over this really quickly. And the thing is, it's nothing magical about it, it's just another way of writing complex numbers. Okay, so, I mean, it is important for us to know, and you'll see why in a few minutes, it is important for us to know what is the phase shift between your voltage signal and your current signal. Okay, so because math is like this, or I don't know, electrical engineers are like this, they like to think in terms of a complex plane. So we normally think of if your current and your voltage were in line with each other, or in phase with each other, then your signal, your voltage, RMS, will be right on the real axis. So they like to think of this as the real axis, and they like to think of this as the imaginary axis. And then this is your phase shift angle between your voltage signal and your current signal. Okay, so we write this, in this case, I'm thinking in terms of voltage, so I guess I'm saying that my current, I'm taking as for granted that my current is, has a phase shift of 0. And so I'm looking at the voltage as my voltage as a phase shifted from my current, and we use this phasor notation. When I say something's a phasor, I put this little hat on it. All this is saying is I can say that this can be written as VRMS, and if I'm writing in polar notation, I would just write raised to the E times my phase shift times the square root of -1, or my imaginary number. If I'm writing it in in Cartesian coordinates, I'll say VRMS cosine of phi, and I'd call this my real part, plus VRMS sine of phi times j, and I'd call this my imaginary part. And the only clever thing that electrical engineers came up with is they said rather than writing this E and superscript, they're just going to write it as VRMS, and then they just make an angle symbol and put your phase shift there. And you're just supposed to know that that angle is the same as E times J, and that this angle, whatever angle is here, just gets multiplied by the J. Or I suppose I could probably write down that J is equal to the square root of -1. And the reason I'm using J instead of I is because I'm planning to use I for current. It never works out. You always end up like, then it turns out, but I was using J for mass moment inertia. I mean, you always realize we should have used a different one. All right. Now, if I'm using this notation, and one of the things about this notation is I've lost, when I write my my voltage in this form, I lose my frequency. So I don't have what my frequency is in this form. So if I want to get my frequency back, and I want to move back into the time domain, I can do that, and the result will be, it's the square root of 2 times the real part. So this value, and I'll take the real part of VRMS raised to the E J phi times e to the 2 pi, my frequency T E, and that'll get me back into the time domain. And I have done all of this for voltage. But it's the same for current. Okay, so I used V here. In fact, quite frankly, I could have used A or I could have used B or something else. The reason they do this is because it makes the math easier. It's not that much easier. But, so, let's see if I can fit this all on one page. Okay, so, no, I'm not gonna try to fit it all on one page. All right, so this is phasor algebra. And it'll help if I draw this again, where I have, so this is my, right now, I'm gonna write V RMS, but it really could be any term. This is my phase angle. So if that's the case, and I call this distance, this location A, this value A, this length from here A, this is A is equal to VRMS cosine of my phase angle. And this distance from here to here, which I'm going to call B, lowercase b, is VRMS sine of my phase angle. So let's say I have two phasors. I'm going to have a phasor A hat, and A hat is equal to A plus BJ, which is also equal to the absolute value of A times E to the J theta A, which is also equal to A M, if I'm going to use the phasor notation. And I have another phasor, capital B, and I'm going to say its real part is C and its imaginary part is D. So this will be, nope. Got ahead of myself. Okay, so just looking at this and looking at this diagram, I can now realize that EA, my phase shift A, I can find that as the inverse tangent of B over A, and my phase shift for B is going to be tangent, or the inverse tangent of D over C, my imaginary part over my real part. My absolute value, which is sometimes written like this, is, so AM, which is equal to the absolute value of A hat, is just the Pythagorean theorem. So this will be A squared plus B squared, and for the value BM here, which is the absolute, I did it again. Okay, now that you have all that, doing simple mathematics with phasors turns out to be pretty simple. If I want to add, I just add the real parts and the imaginary parts. So A hat plus B hat is equal to A plus C plus B, no, AC, that's right, AC, my two real parts, plus my two imaginary parts. If I want to do multiplication, written as phasors, A phasor times B phasor, all I need to do is I need to multiply the two absolute values. And then I just add the angles. So I just get my phase angle of A plus my phase angle of B. And if I want to do division, divide one phase angle by the one phasor by the other phasor, then again, I just need to divide my two root mean square values, and then I subtract the angles. So electrical engineers like this notation because of these math tricks. And as long as your signals are not changing in time, and I have to be a little careful with it. It's an AC signal, so it is changing in time. But as long as it's more or less steady state, so you have a constant phase shift and you have a constant sinusoidal pattern, right? And you're not like increasing the voltage or decreasing the voltage over time, then you can use this phasor notation, no problem. If your signal is changing, your voltage is changing in time beyond its normal, it's not a pure sinusoidal, the math becomes more complicated, but that gets beyond what we have to worry about in this class. Oh, I should also point out there's a couple typos in the textbook, which I think I brought with me. They're just, I don't know if I wouldn't call them typos, I call them typographical errors. And what it is the division symbol's missing. So, oh, yeah, where it says phasor division, there's supposed to be a division symbol between the A and the C here. And that got lost somehow. So that's supposed to be a division symbol there on equation 519. And there's another one like that. There's another error like that that we'll see in a minute. All right. So with that in mind, I'm now going to bring up the concept of complex impedance. And I know you've seen complex impedance before, but this is going to give you a new way to think about it. Okay, so we talked about in inductive circuits and in capacitive circuits, we have this concept of reactance, and reactance acts like resistance. Impedance is a complex resistance, which includes the resistance of any resistors you have in your circuit, plus the reactance of your circuit that you might have because it's an AC circuit and you have any resistor or any capacitors or inductors in your circuit. So I could write this as Z equals my complex impedance is equal to my resistance. And I wrote resistors up here, I meant to write resistance. Plus 2 pi FL from my capacitors minus 1 over 2 pi FC. Oh, wait, no, I'm sorry, this is from my inductors, this is from my capacitors. Okay. And the negative is because, remember, one's going to force it to be phase shift in one direction, one's going to make it phase shift in the other direction. Okay? So, and another way I could have written this is resistance plus XL minus XC J. So, using the way electrical engineers like to think, I can think of, I have my impedance is the absolute value of this imaginary number. So this is my ZRMS, my root mean average impedance. This axis, this real axis, corresponds to my resistance. And my imaginary axis responds to my reactance, corresponds to my reactance. Now, the nice way of thinking about this is that in thinking in terms of impedance instead of resistance, is now I can still use Ohm's law. Or at least an analogy to Ohm's law, where my voltage in phasor terms is equal to my current in phasor term times my impedance in phasor term. Or if I like, which is this is the way I'm used to seeing Ohm's law, is that my current is equal to my voltage divided by my resistance or divided by my impedance. Okay? And then the same laws that series laws and parallel laws that apply to resistors also apply to impedance. So in series, I have my impedance total in series is just equal to the sum of all of my individual impedance in series. And if I have in parallel the same rule, if I have various things with impedance in parallel to each other, it is the reciprocal of the sum of the reciprocals where this is all of the, I'm summing up all of the things that are causing impedance that are in parallel with each other. And again, there's a typo in the book. So if you're looking at this information in the textbook and you're looking at this equation on page 210, where it says 1 ZI, there's supposed to be, it's 1 over ZI. And for some reason, there would have been no reason to say 1 times ZI, right? But it should be pretty obvious that was an error, but, all right. Also, if I need to, and I want to analyze my circuit, all my Kirchhoff's laws, or both my Kirchhoff's laws apply. Oh, I need to zoom back out. Sorry. All right. Now, with this in mind, we can start talking about some issues you have to concern yourself with when you're talking about power in AC circuits. It turns out that the power that you think you have, the power that you think you're consuming, might not actually be the amount of power you actually are creating or you are consuming. So this next section, this is power in AC circuits. Okay, so we have these, there's 3 different kinds of power that you need to worry about. There's real power and there's apparent power, and there's reactive power. So the real power is what you're actually consuming. what you're actually consuming in your appliance, I should say, what you're actually consuming or generating. Incidentally, what's power in electrical systems? I said this a lot early in the course. Remember, we're converting, I say, where the power in the wind is 1/2 rho, your area times your power code, or I guess in the wind is 1/2 rho, your area times velocity squared. Then you're converting that into mechanical power. Mechanical power is torque times speed. And then the generator is converting that into electrical power. And electrical power is measured in watts. And how do we get watts?
Times rotation, revolution. Volts times amps.
Volts times amps.
There you go.
And yes,
I don't know.
that was a gotcha question, because I was looking for volts times amps. However, that is not our real power.
Yeah.
Okay? What that is our apparent power. Apparent power we will get apparent power, and we're going to use the letter S for apparent power, and that is equal to our voltage, our root mean square of our voltage, our average voltage, times our average current. And of course, it's measured as volts times amps, or watts, if you like. All right. The apparent power will only be the real power if the voltage and the current are in phase with one another. But as I said, normally they're not. So, our real power, and I know I already wrote it down, but I'll write this again. Real power, I'm going to say what an appliance is consuming, or a generator is producing. And that is equal to, so we're going to use P, or real power, and that is equal to VRMS times IRMS times the cosine of the phase shift between the voltage and the current. This term here, cosine phi, is referred to as the power factor. And current flowing in any type of inductive or capacitance resistance does not result in real power, but results in reactive power. So reactive power which has to do with the amount of current that is currently flowing through an inductor, and therefore generating a magnetic field. Or is in a conductor and it is also therefore generating an electric field. This is called reactive power. We're going to use the symbol Q, and it is equal to VRMS, the current RMS, sine the phase shift. And typically, we write the real power, we'll say this is in watts. And really, all of them are in the same units. So we call it, apparent power, volts, amps, power, watts. Often, we refer to the units, even though it really is watts. It's volts, amps, reactive, or VAR. So if you see a VAR reading, and sometimes if you're ever walked around your neighborhood, I feel like I saw these a lot in Florida. I don't know if I see them around here. You know, like every once in a while, like you see a big power box, like just on your neighborhood,
Yeah.
and it's like a little transformer for your little block or 2 or 3 block area. And it'll say something like bar on it and it'll have a number. And it also has the power factor sometimes on it. And that's what bar stands for. It is volts active, amps reactive. So you can see the same logic we did before, where you have your apparent power, which is what you think you have, is your hypotenuse. Your real power is your real axis, and your imaginary axis is your reactive power. And so your power factor which I previously defined as cosine of your phase angle, is also, it's your real power over your apparent power. Now, I still find some of this stuff really confusing. So, I found a really good YouTube video, which I think explains this really well. So I'm gonna switch gears and turn off the document camera. I'm gonna go to the computer, and we're gonna watch this 9-minute video together. That I think really helps explain what's going on in really simple terms. And I hope you guys will agree with that. Oh yeah, this makes it a lot more clear. All right, so again, this is on Canvas. So I thought I posted this a few days ago, but I realized I forgot to publish it. So it just became available just now. So under week 11, which you guys should now have access to, and I'm in student view, so there is a list of good videos for understanding electrical concepts. And I click on here, and the very first one, understanding real power, reactive power, and apparent power. I'll go ahead and click on that. And I'm going to hit, and we're going to watch a commercial.
After years of swiping right on human garbage,
Because
In an AC circuit, the voltage and current keep changing direction. Voltage is the energy per charge, and we can visualize the energy as boxes attached to the charged particles. The higher the voltage, the more energy per particle. Here, we have an alternating voltage, but there is no current, and hence there is no flow of energy. Here, we have an alternating current, but there is no voltage difference. Hence, there is again no net flow of energy. This is because the number of energy boxes flowing to the left is exactly equal to the number of energy boxes flowing to the right. To have a net flow of energy, we need both a voltage difference and a current. Notice now that although the flow of the particles keeps changing directions, there is always a net flow of energy boxes from the left to the right. So far, the net flow of power has been equal to the RMS voltage multiplied by the RMS current. However, this assumes that the voltage and current are in phase. Consider now what happens when the voltage and current are 90 degrees out of phase. Now, over time, the net flow of energy boxes to the right is exactly equal to the net flow of energy boxes to the left. In other words, even though we have an AC voltage and an AC current, there is no net flow of real power. We say that the apparent power is equal to the RMS voltage multiplied by the RMS current. But for the real power to be at its maximum for a given voltage and current, the voltage and the current need to be in phase with one another. As the phase difference changes, the apparent power stays the same, but the real power changes. The phase difference between the voltage and the current is equal to the angle of this triangle. When the phase difference is 90 degrees, the real power is 0. When the phase difference is 0, the real power is at a maximum. If the voltage is 0, then both the real and the apparent power are 0. Similarly, if the current is 0, both the real and the apparent power are 0. The apparent power is equal to the RMS voltage multiplied by the RMS current. The real power is equal to apparent power multiplied by the cosine of the angle representing the phase difference. The cosine of the angle is what we call the power factor. The vector on the right of this triangle is what we refer to as the reactive power. The actual real power is the length of the bottom vector in this triangle. When the phase difference is 90 degrees, the real power is 0. Without changing the magnitude of the current or the magnitude of the voltage, we can increase the net flow of energy by making the voltage and the current more in phase with each other. Having the voltage and current be more in phase with each other is desirable because some of the energy is lost in the resistance of the wires. The energy lost in the resistance of the wires depends on the resistance and on the magnitude of the current, regardless of the phase difference between the voltage and the current. Therefore, if the current and voltage are more in phase, we deliver more energy for the amount of energy lost. In other words, the more the voltage and the current are in phase, the more efficiently the electric power is delivered. Much more information is available in the other videos on this channel. Please subscribe for notifications when new videos are present. And if you're able to, please consider supporting us on.
And don't forget to smash that like button.
Hit that bell.
Hit that, right, yeah. I've been told by my stepson, this is he gets very upset that I don't do this in the videos. You have to say smash the like button. Yeah, yeah.
I know you did.
All right. Okay, I want to do a quick example of how of putting all this stuff together. So one last little bit of terminology. Again, so this angle, which is our phase shift, we can also call it the power factor angle. And if this is greater than 0, we say our power factor is leading. And it's current, and by leading we mean that current is leading voltage. And if our phase shift, if our phi is less than phi is less than 0, we say power is lagging, or power factor. Or power factor is lagging, and what it means, that means is current is lagging or behind. All right, so now I want to do this example, and this example is in the book, but it's like 3 lines in the book, and it's a little confusing. So let's say I have a circuit, and I have an AC voltage source, and my voltage is equal to, let's say 100 volts, and my phase shift is 0. I'll rewrite that. Is 0 degrees, okay? And in this circuit, I have a resistor, I have an inductor, and I have a capacitor. And my resistance, I can rewrite the resistance as impedance of a resistor, and I can say that, measure it just like I normally would for in real space. I just say that it's 4 ohms. Okay. And let's say I can write the impedance in my inductor as having 3 omega, where, 3 ohm, actually, it's 3 and it's imaginary. So this is, remember, this is reactance. So it's 3 and it will be an imaginary space. So I put the J there, and then I can also write it as ohms. And I can write the impedance of my capacitor is equal to -6J. It is also reactance. So it is imaginary, 6J ohm. Now these are all in series. So I can add them together and say that my total impedance is simply the impedance of my resistor plus the impedance of my inductor plus the impedance of my capacitor. And that will just be equal to 4 plus 3J minus 6J. Which I can write as 4 minus 3J. Now if I want, and I do, I can write this in phasor form. I write this in phasor form, I need the absolute value. My absolute value, remember, is the square root of my real part plus my imaginary, the square of my imaginary part. So this will be equal to, in phasor form, of the square root of 4 squared plus 3 squared. Technically, it's plus minus 3 squared. But it's, just to, in case anyone gets confused about order operations, okay? And then the angle is going to be the inverse tangent of -3, which is my imaginary part, over my real part. So 4 squared is 16, 3 squared is 9, 16 plus 9 is 25, the square root of that is 5. Probably tell why I chose these numbers. And if you pull out your calculator, you will find that this is equal to -36.9 degrees. Unless you're in radian mode, in which case you'll find that it's something in radians. So, if I want to find my current I phasor is equal to my voltage in terms of phasor times my resistance as a phasor. And remember, I said when you divide two phasors, what you do is you divide their absolute values and then you subtract the angles. So my absolute value of my voltage was just 100 volts, and it had 0 phase shift. Divided by my absolute value was 5 ohms. Times, or not times, but then my angle, I subtract my angles. Well, my angle that went with my voltage was 0. Minus, and remember I had a minus 36 here, so this is minus 36.9. And so I end up with 100 divided by 5 is 20. Divided, and then my phase shift is 36.9. And so that's my current. Now to find my real power, I can do that 2 ways. I can find my power real, and I can find that from the absolute value of my current squared times my resistance. You guys remember this alternative way to find power? is your current squared times resistance. Okay, it's the same thing, except now this is a complex number, so you take the absolute value of the complex number. This will end up being, since we have this value, we found this was 20, this will be 20 squared times my resistance, which was 4, and this is R, this is not my impedance, this is R, my resistance. Okay, so this was in the original problem statement 4. So 20 times 20 is 400, times 4 is 16, I'm gonna get 1600 watts. Or, I can also find my power real is equal to the absolute value of my current times the absolute value of my voltage, my current RMS, my voltage RMS, times my power factor, which in this case is cosine of 36.9 degrees. This value we've already established is 20 amps. This value we found was 100 volts. 100 times 20, that should be 2,000. But it's not 2,000 because we also have to do the cosine of 36.9. And you should find that that also works out to 1,600 watts. Or pretty close. We may have rounded a little bit on that 36.9. All right. So that's an example of all that. The next thing I want to cover, and there's no point starting because I'm not going to have time to go any further, is three-phase power. Okay, so that is just a couple pages, and then we'll start in the fundamentals of electromagnetism, and that'll help us understand how different generators work. If you want to get a head start on how different generators work, many of the other videos I posted I have I have a couple of them on three-phase powers. I have one on DC generators, which I assume is review for you guys, but it might be nice to kind of review it. And then I have a video on AC synchronous motors. I posted a video on asynchronous or induction motors. And then this last one is not really important for this class. I just thought you might find it interesting. Explains how in the United States, we actually do have 240 volts coming to our house, but it gets split into 120. And I thought you guys might find that interesting. So I think I'm going to wrap it up for today. Are there any questions about projects, about homework due on Friday, about life in general? 42. I'm that big a nerd.
Yeah.
And I grew up in the 80s, so.
Well, no one has any questions. I do. Forrest is worried about the bearings in his motors, the wind project. As far as them holding the whole load. This is for the wind turbine competition.
Yeah, no, I get that, but Forrest?
Forrest.
Oh, yeah, Forrest.
We can call him Forrest. But is that something we should be worried about? Like, should I have another bearing to take that load? Do you think?
Oh, nice.
I think you definitely have you definitely need to be concerned with the load on the
horizontal on the bearing.
Yeah, I understand what he's saying. Like, if things are gonna put, and it's gonna be like,
they're not designed for that.
yeah, that is something.
Okay. Do you think the pillow block is appropriate, or should I actually do like a thrust bearing?
Everything outside of mine.
Okay, a pillow block is just
That is a Dr. D question.
okay, we're literally studying it as class.
As far as like
Do
as
message.
far as like what type of bearing stuff, that is very difficult.
Okay, the sad reality is, it's like, you can go on Amazon, all day long. And what we're learning in your class is like, you take the rating from the bearing and you can do this math to figure out which bearing you need. We don't get any of that information from Amazon.
Oh,
So that's why I'm trying to
so,
get a feel for like,
if you talk to Derek and you ask Derek for, if he show you the McMaster catalog.
okay,
If we order stuff from McMaster, sometimes we get it same day. It's almost always next day or same day, depending on what time you order
well, I
it.
should have done that.
And the McMaster catalog is gonna have a lot more information than Amazon.
Yeah, probably. Okay. Yeah, because I'm trying to do yaw system now.
Okay.
Yeah, so.
Dr. Tuck, I'm gonna send, President Dr. D and you, and Dr. Fu all in your note, just to double check. Next Friday, I will be in class at least for my morning.
Yeah. Yeah. Should I get you also started part I got the CP value.
For CF.
Oh.
Yeah, you did the first
CP.
part. Yeah, I skipped that and I did the next one, right before that, I got the CF.
Okay, is that the one you have to go through the whole Excel file?
Yeah, I downloaded the Excel file and did stuff.
You did it?
Yeah.
Okay. Yeah, I opened the Excel file last night, I was like, oh my god, what values am I supposed to use?
Yeah, you kind of had to read the problem, but most of the columns you don't use.
Okay, cool. So we're reading up like some kind of shit.
Maybe I remember the smart building on Friday to the this class.
Yesterday I got in, I got started on